So good afternoon, everyone. Thank you for the introduction again. Well, let's just move here very quickly. As was previously introduced, I'm a research fellow in multiple affiliations. So I'm currently at MIT Boston, but I'm also a researcher at University of Bologna, Italy, and a visiting researcher at TU Braunschweig. My whole research is about how to apply steel 3D printing in construction on multiple levels. And very recently, I've also moved towards other materials and other construction materials. But my background is actually as a structural engineering. So I am a structural engineer indeed. And my previous background was an earthquake resistant design. So it's kind of, I was just jumping into additive manufacturing construction for my PhD. So I will just move very quickly to give you an overview to metal 3D printing in construction. I know that most of you maybe already know that. So over the last decade, metal 3D printing in construction was paving its way first for small connections and very few details in high-end and high-appealing architecture applications. But only over the last 5 years or so, there was the beginning of applying wire and arc additive manufacturing, so an arc-based direct energy deposition, to increase the scale of applications. So as you probably already know, so wire and arc additive manufacturing, it's a weld-based additive manufacturing technology. So it makes use of off-the-shelf welding equipment mounted on top of a robotic arm, and it allows to actually increase the size of the printed element up to a few meters of height and several meters of length. So this is, of course, one of the advantages. So, of course, it's a fast production, but also, ideally, there is no constraints in geometry to be printed in shape or size, and high resistance of the material to be printed. Of course, there are still issues to be tackled. So, the lack of material characterization and mechanical predictions in terms of the performances, and current standard design guidelines. So why making use of wire and arc additive manufacturing construction? So one great advantage is to actually make use of these freedoms. So the idea is that you can ideally create geometries and use material only where it's needed. So make highly efficient structural elements by severely reducing the material use. On the other hand, you need an interdisciplinary effort to do so. So it's not just structural engineering anymore, but you actually need to consider fabrication, design, testing, verification, and robotics. So what was my aim during my whole research was actually to try to draw guidelines, structural design guidelines for wire and arc additive manufacturing elements. So conventionally speaking, Eurocode's current standard building codes make use of conventional approaches, so partial safety factors and design values that are calibrated, accounting for an isotropic behavior, linear elastic material, and ideally like a deterministic geometry, meaning that your geometry is ideal. This is not true for WAM. This is not true for additive manufactured pieces. So one way to go would be to go with advanced numerical modeling. So having a whole digital twin of your entire structure and perform what it's called design by testing. But this is not feasible for every type of project. So it can be done for very high-end projects, but not for everyday use, let's say conventional use. So my idea was actually to adapt the conventional design approach to WAM. So how to do so? Well, you first, of course, recalibrate the design values and the partial safety factors. You account for the anisotropy of the material once it's printed, and you also account for the geometrical irregularities. So this is a little bit of an overview of my previous work on WAM. So we started 6 years ago at the University of Bologna, Italy. We started by material characterization because we honestly first wanted to know how like this material worked and how much it would get in terms of strength. I mean, we're engineers, so we really want to know in the end if it's strong enough for our constructions. The result was surprising for us because we didn't expect back in the days that the material would be so high anisotropic. I'm talking about stainless steel, and in particular 308 LSI. And in this case, we then like matched our results also with the metallurgic department, and we actually saw that it was all in terms of the microstructure. The microstructure for these layer by layer deposition created like this grain orientation, and so the grain orientation was what made the printed stainless steel piece to be highly anisotropic, and in particular to be orthotropic. So we then could predict the material by creating an orthotropic material model, and we could then engineer our elements by taking this into account. Not only that, so of course, as I said before, WAM elements are highly irregular in terms of the geometry that it's printed. So there is an inherent surface roughness, lack of straightness, but also thickness variation, diameter variation, geometry variation. So of course we need to calibrate that and to characterize that properly if we want to then make assumptions for our design afterwards. So we did that through 3D scan techniques, predictions, finite element modeling, and we tried to came up with strategies to, again, make use of that for our design purposes. And here comes with the design. So first guidelines were drawn for some companies that we partnered with, but not only that, we actually were willing to, to also open this up more for maybe ASTM or like future, standard guidelines for additive manufacturing construction. So the idea here is really to recalibrate and recreate like design values, characteristic values of the material strength based on the anisotropy of the material, and also create possible solutions to overcome this real inherent geometrical irregularity by having a volume equivalency to have like a uniform geometry along the piece. As I said before, so we created like an orthotropic material model. So we were also able to engineer this material by creating like optimization studies for optimized, efficient beams. In this case, this was a case study on new optimized IPE beams. We called it a blended optimization in the sense that the pure topology optimization algorithms are blended by having, like within our basic principles of structural engineers, manufacturing constraints, anisotropy of the material, and final use. So the final result was actually able to sustain different load cases and different boundary conditions for real case applications. This is just like a hint. So one idea that we had was to actually create a first prototype for an integrated mobile 3D printing system, which is able ideally to 3D print on the element while moving on it. So it's actually currently under patent protection in Italy, and we are quite proud of this like first small rabbit over there. These are just some of the projects that for which we were able to actually grow this research. I would like to just point out the address, which is the second last, and it's a Erasmus Plus project to create a course on additive manufacturing, and the TRR 277, it's additive manufacturing construction. It's a collaborative research project from TU Braunschweig and TU Munich, and it's really just on additive manufacturing construction on multiple ways. Now moving to the core of my presentation, so dot-by-dot printing for lattice structures. Dot-by-dot printing is one WAM technique, so the idea is rather than going layer by layer, you're going towards multiple droplets of molted metal, one on top of the other. So the idea is to create grid shells, grids, bars, and lattice systems. There are, of course, issues to be tackled. So, of course, there's the influence on the build angle. So similarly, but not really to the anisotropic behavior. In this case, the higher the build angle, the higher also the geometrical irregularities and the lower the mechanical properties. So this is, of course, needs to be taken into account when you are designing grid shells and lattice structures. But why doing that? Well, of course, there's a huge chance of having, again, like exploit this use and like this freedom by creating like highly efficient elements by reducing the material use severely. But of course, there's still like the current issue is the long printing time. Why lattice elements? Well, we all know that they are highly efficient. So at the micro scale, so at the scale of the single material, we all know that like lattice elements are well renowned for high stiffness and low material use. At the macro scale, as engineers, we all know about truss elements and truss systems, and these are again very good for the high stiffness and low weight, so low material use again. So our idea was actually to scale that up to the mesoscale, so to the scale of the single element. And we could do that only thanks to WAM, because that way we were overcoming the issue of the connection between the single elements at the macro scale, but we were also increasing the application use of the lattice elements at the micro scale. So we started this research in 2018 thanks to MX3D, where I was intern there. The first idea of the diagrid column was actually awarded the 3D Pioneers Challenge 2021 with a special mention by Autodesk for the design. And we continued our research at TU Braunschweig, and very recently we also presented a patent in Italy. We knew that we needed to tackle the issue of different build angles and hence different material properties and different geometry, different irregularities in terms of geometry. So we first characterized the three types of inclinations. So the vertical ones, the bars printed at 10 degrees and the bars printed at 45 degrees. 10 degrees was like actually like one of the lowest possible degree angle, and 45 degrees was actually the highest one, up to which the quality was not really feasible for construction. So moving fast, the experimental tests were actually carried out first on the geometrical characterization. So again, of course, we first wanted to understand what were like the diameter variations and the lack of straightness, and we characterized the eccentricity of these bars. Of course, no surprise, the one with the higher degree, like the higher build angle, resulted in the higher irregularity. Same goes for the mechanical properties. So of course, a higher build angle resulted into lower mechanical properties. But now moving to the fabrication, because it's the thing that I think you would like most. So as I said, there are different ways of producing lattice elements at the mesoscale. So you can either just do an external diagrid or also do a full 3D diagrid. It depends on, of course, the type of stiffness that you want to achieve. The printing time can be long, that's for sure, so you need to also consider that, and the manufacturing constraints. So as I said, maximum inclination of the bars, but also the limitation in the maximum free length of the single pieces to avoid local buckling. The organization is drop by drop. So dot by dot means drop by drop, and each single drop of molten metal results in a sequence, of course, of rules for the robot. So you need to tackle like the offset of each single dot, but you also need to understand what is the waiting time between single dots. Cold metal transfer is of course preferable, as well as eye accuracy of the robotic arm, because of course, given that it's a dot by dot system, so each single drop you have to have an accuracy on your like the positioning of your robotic head up to 0.5 millimeter, both in terms of like on the plane, but also in terms of layer height. Now going to the case studies. The first one was actually the diagrid column. I would have hoped to actually tell you that you could have seen that in the MX3D booth. Last year and the previous years, it was always there. Not sure why this year that I'm presenting this is not here. But anyway, I hope you will see in like multiple pictures. Anyway, this is actually a half-scaled column. It's a 2 meter high and 25 centimeter in diameter. It was really the first proof of concept of a die-grid element that could be printed and could actually have very good utilization factor while having a reduction into the material that it's used, so a reduction in weight. The further case studies were developed at TU Braunschweig within the TRR 277 project. So we actually tried like multiple experiments and small prototypes, smaller scales, until we wanted to go big. And we actually created the first base part of a proof of concept of a 12 meter high 3D die-grid pillar. Of course, it's not, I mean, it's just a proof of concept, but it would be feasible to print it in pieces. Last but not least, it's something that I'm very proud because it recently received also the iconic award here in Germany for the disruptive concept, and it's the so-called flow wall. So the idea here is to combine different additive manufacturing strategies. So in this case, WAM as a reinforcement and shotcrete 3D printing as actually the concrete matrix to create adaptive coastline protection systems. So in this case, we are actually making use of the freedom in the geometry to be printed, but also combining the use of two different additive manufacturing techniques. So what's next? Of course, this is just the beginning to me of applying metal 3D printing at a very large scale. I see here at Formnext that there is an increasing interest in WAM, which I'm very happy to know of. But I think that in this case, sky is not the limit, so we should also dream bigger and go bigger. So with that, I also thank you. And this is just a list of significant publications. So thank you.
Are there questions in the audience? Yes, one here.
Hi, thank you very much, Vittoria, for your amazing work as usual. My question is, would you ever think about, say, distributing the thickness of the actual droplets? So say, adding more droplets in a specific spot to increase the thickness of the struts, and use this as a method of, say, having more, say, functionally graded materials as lattices? Or is it something you haven't looked at?
Yeah, no, that's a very good question. So let's say not just regarding dot-by-dot printing, but in general, I think that like for WAM as application, rather than just going very big into the fabrication, we should also consider using a sort of hybrid manufacturing. So exactly, like stiffening maybe like conventional members by just applying WAM where it's needed. Or yeah, why not? Also for grades, I think it would be used for retrofitting or for functionally graded, as you said. For the moment, it's kind of hard to print the bars at different diameters, so like to actually have like a variation in diameters and so the thickness of the lattice element itself. But I think you can also work on the density of the die grid, which is something that it's way easier to actually design.
Okay. Yeah. Thank you.
Sure.
So if you have dot-to-dot a die grid or grid or whatever, in what way are you limited by the machine itself? So is there innovation like with, if you have a die grid, you have like 50 points, would you not need a machine with 50 points in the same time then? Or is there work in this direction as well?
Yeah, I mean, I think there is for sure growing interest in this, like in the dot-by-dot technique. So I think like there should be also like some advancement in the fabrication. So currently what we are doing is to go like each single layer. So like, let's say that like each single cross section has 50 points, then like you're printing 50 points, but maybe you're optimizing the path planning so that like you're reducing the motion of the robot. And so you can optimize that. And so you're reducing also the printing time. But Yeah, for sure. There could be limitations that can be also overcome quite easily. So like you can maybe weld pieces together afterwards. And so like you can actually increase the scale of your printed part even more.
Can I ask one more question?
Yeah.
So if you look at relativity space, are they using WAM as well? And are they using one nozzle, or have they solved some kind of economics puzzle?
Do you mean in space?
So they print steel rockets, basically.
Yes.
Do you know them?
Yes, I know of them. I don't know the project personally, so I think there is for sure also there are some advancements that maybe they're not disclosing yet for the public. But again, also for aerospace, I know that there's like an increasing interest, especially for like this way of like reducing the material use and looking for like a reduced weight of the pieces. So that's for sure. Not really sure about the fabrication though.
Let's find out. Yeah.
Maybe one question just to connect a little bit to the conversation of Matthias's presentation actually earlier. The question of do you see retrospective or retrofitting potential for this? So rather than making entirely new structures to go in and adapt existing structures or correct or to fix.
For sure. So like one way to me to exploit the lattice meso elements would be to retrofit maybe like on a on-site fabrication the current columns for existing buildings so that they might need, you know, the external steel cage for increase the strength of them. But not only, like as I said before, you can also make use of WAM to increase maybe like the stiffness or the strength of existing members, existing steel members where it's needed. So yes, that's for sure.